my dear students, so KCET 2025 examination is very close and we have relaunched our KCET Masterstroke series, and in today's video we are going to complete in one shot the chapter D and F block elements. So let me tell you, this is a very important chapter for KCET, so definitely you have to focus on the trends, the properties part of this chapter. So I'll be discussing that in detail, and other introduction and part we will just revise and move on. Okay, so let me tell you first what all things are there in this video. So the first thing that we are going to study here is the position in the periodic table. So where is exactly D and F block elements located? Second, we are studying about the electronic configuration. Third, this is very important, that is your general trends. Here I will be discussing almost 15 trends that you should revise, you should practice, you should understand the concept here very well. Next we will talk about the important compounds, you know, KMnO4 and K2Cr2O7, their preparation method and their oxidizing properties. Next we have here lanthanoids, and then we have actinoids. Okay, fine. So now just a minute. So now let us start with the first topic, that is position in the periodic table. So what exactly the D block elements mean? The D block elements means the last electron will enter the D and the F orbital. Okay, so you know the S, P, D, F orbitals are there. So the last electron of an atom, if it is entering to the D orbital or it is entering to the F orbital, then we will call it D or F block respectively. I hope this is clear. This is applicable for all S block, P block, D block, F block, everything, everywhere that is there. Now the D block, which all groups are covered in D block? Group number 3 to group number 12. And in F block we have the 4f and the 5f orbitals are progressively filled. They are placed in the separate panel at the bottom of the periodic table. So if you have seen the periodic table, after the whole periodic table below we have two rows. Okay, that is your lanthanoids and actinoids series. Clear? Now what is this transition metals? Transition metals, D block elements are called as transition metals and F block elements are called as inner transition metals. Okay, moving forward here, we have that 4 types of transition metal series are there. The first one is your 3D series, scandium to zinc. Then we have 4D series, that is your Y to cadmium. Next 5D series, lanthanum to hafnium, lanthanum and hafnium to mercury. So lanthanum is actually not a part of the lanthanoid, but it is the first element before the lanthanoid series. So we consider, or the properties matches, so it is studied together. Next, for 6D series you have actinum and then RF to CN. So you don't have to remember all this, but you have to just know the elements of 3D series very thoroughly. And then you should be knowing for actinoids and for your lanthanoids. Okay, now coming to inner transition. So inner transition metals, you have cerium to lutetium, 4f elements. Actinoids, you have thorium to lawrencium, that is your 5f elements. So these are elements, which one you have to remember? Let me tell you. For 3D you have to remember, then you have to remember for 4f and 5f, right? 3D starts from scandium to zinc. Okay, then 4f is from your cerium to lutetium and 5f is from thorium to lawrencium. Clear? Okay. Yes, you can see the elements here. I can say the general electronic configuration is given. Okay, and the elements first and the last series first and the last element list is given. Okay, fine. Now you can see the periodic table. Let me explain to you very clearly this part. Okay, this part is called as your D block, this middle blue color series. Okay, now here you see scandium. So this is your first period, second period, third period, fourth period, fifth period and sixth period. Okay, so fourth period is your 3D elements, fifth period is your 4D elements and sixth period is your 5D elements. Now here you have to remember that from 57 to 71. Okay, so lanthanum is actually a part of this D block elements, right? So lanthanum, then from 58, that is cerium, to 71, that is your lutetium, these are your lanthanoid elements. So after that comes 72, so 72 to 80, and then here we have this 57, that is lanthanum. Okay, so these are your, I'll say, that is your 5D elements. Okay, next one, this is your lanthanoid series and this is your actinoid series. Okay, Moving forward here, the position in periodic table. So what exactly is transition metal? So if you understand what is the definition of transition metal, very simple, that the transition element should have their d orbital partially filled. So d orbital can hold 10 electrons, right? So if it is not holding 10 electrons, then it is a part of transition element. Now when it should not hold 10 electrons, it should not be holding 10 electrons in its ground state, okay, ground state, and common, sorry, not and, or common oxidation state. Okay, so if there is no completely filled d orbitals in the ground state or in the common oxidation state, then we will call it as a transition element. Here one exception comes, or you can see for zinc. The zinc electronic configuration, I know all of you will be remembering, but still let me still recollect, that is 3d10 4s2. This is the ground state electronic configuration. Now Zn2 plus will be equal to 3d10, right? So in the ground state and in the common oxidation state, it has completely filled d orbitals, right? So that's why I can say that zinc is not a transition element. Is it also not a d block element? No, it is a part of d block element, but it is not a transition element. Okay, so generally such elements are called as pseudo transition element. I hope this is clear. Pseudo transition element. So what all elements come in the pseudo transition element series? You have zinc, you have cadmium, and you have mercury. So these three elements are d block elements but not transition elements, and they are called as pseudo transition elements. I hope this is clear. Okay, so from here questions can be asked, so please make sure that you understand this concept properly. Now electronic configuration I am not going to teach you, but yes, you have to remember for scandium to zinc electronic configuration, definitely you have to remember, otherwise you will not be able to solve questions based on color, magnetic moment. So many properties are based on this electronic configurations, right? So please remember, if you haven't, today itself you complete this task. From scandium to zinc, all the electronic configuration should be completely remembered. Okay. Moving forward here, physical properties, very important. I told you almost 15 properties we have to discuss, right? So let me just show you. Please make a list of this, and I'll be giving you the what exactly you should be knowing. So first we'll be talking about the physical properties, means what how a transition element looks, what is its density, what is its luster, what is its color. So physical appearance, based on that we'll have certain discussion. Then we'll talk about the enthalpy of atomization, atomic and ionic radii, ionization enthalpy, oxidation states, trend in M2 plus to M reduction potential, trends in M3 plus to M plus 2 potential, then trends in the higher oxidation state, magnetic properties, colored compounds, complex compounds, catalytic properties, interstitial compounds, and alloy formation. These all the things are very important and the core topic of this chapter, so please do not ignore this. You have to understand with me every 14 properties. Okay, let's start with the first thing, that is your physical properties. So physical properties means we want to say how exactly the physically a transition element looks. So the first thing is they have very high tensile strength. They are ductile, because you know metals have a property of ductile, right? You can convert them into thin wires. They are ductile, they are malleable, okay? They have high temperature, thermal and electrical conductivity, that is also there. They have a metallic luster, because they are what I'll say, they are metal, so they will have a lustrous property. Then they are very hard, except, so please remember this one, the exceptions in the DNF block are very important, or else you can say in inorganic chemistry itself the exceptions are very important, right? So generally the transition metals are very hard, but what are the exceptions here? We have zinc, cadmium and mercury. These are not hard metals. Why? We will know in the next session. Okay, for now please remember this one. Next we have high melting and boiling points due to the metallic bonding. Here also we have an exception, that is magnesium and technetium. Okay, sorry, not magnesium, manganese and technetium. So I am going, let me explain it here onwards, here only, what is the conclusion or what is the reason of these exceptions. So first of all, why the metal is very hard? The metal is very hard, generally the transition metals are very hard because of strong intermolecular forces. Okay, strong intermolecular forces. What type of intermolecular forces are there? They have strong metallic bonding. Okay. Now, what is the reason of this strong metallic bonding? We have unpaired electrons. Okay. So we have discussed that transition elements are those elements which do not have completely filled d orbitals, right? If it is not completely filled, it will have unpaired electrons. If it is having unpaired electron, then it can make metallic bonding, and that is why the intermolecular force is very high, and that is why the metals are generally very hard. But what happens in zinc, cadmium and mercury? I think by now all of you can guess it. In zinc, cadmium and mercury, definitely there is no unpaired electron, so there is no metallic bonding, so that is why the bond is very weak. Okay. Next we have here high melting and boiling point due to the metallic bonding. So generally due to this, the another consequence is they have high metallic bonding. That is why the atoms are very tightly packed, and that is why the melting point and the boiling point is very high. But here also we have an exception, that is your manganese and technetium. So if you see manganese, okay, manganese has an electronic configuration of 3d5 and 4s2. And 3d5 looks like this, right? Now a question may arise that, ma'am, it is having 5 unpaired electrons, right? Then it should form very good metallic bonding. Then why does it have a low melting point? So dear, see, if it is partially filled unpaired electrons, here d5 is there, no doubt there is unpaired electron, but this d5 is a magical number. What is it? It has it is considered as a stable half filled configuration. Okay. Now because of this stability, these electrons are very strongly attracted towards the nucleus. Okay. Now when it is very strongly attracted towards the nucleus, it is not available for your metallic bonding. So even though it is having unpaired electrons, but it is a very stable configuration, and that is why these electrons are strongly attracted towards the nucleus, and that is why it cannot form metallic bonding, right? So that is why there is unpaired electron. So what is the case of manganese here? There is unpaired electron. Okay, unpaired electron is there, but it has no metallic bonding. Why? Because of stable half-filled configuration, right? Okay, next, I hope both the exceptions are clear to you, so please mark them. Next we will move to yes, okay, just a minute. Yeah, you can see here, this is your melting point and boiling point graph. So you can see manganese is having a dip in the melting point. So as we move along the period, the number of unpaired electron increases. I hope all of you will write the electronic configuration and check this. As I am moving along the period, the number of unpaired electrons are increasing. The magnetic, or I can say the intermolecular forces or the metallic bonding is increasing, so melting point is increasing. But when manganese comes, although it is having unpaired electrons, but it is a stable half-filled configuration, so electrons are attracted very tightly towards the nucleus, so they do not form metallic bonding, so their melting point drops here. So after manganese, again it rises. We have iron, cobalt, nickel and copper, then iron, nickel, cobalt, and then for copper again it dips. Clear? So that is again the reason for copper is it is having 3d10 configuration. 3d10 configuration means no unpaired electron, so melting point will decrease. Okay, so that is what the graph says. The same thing applies for technetium as well. Okay, next we can see the enthalpy of atomization. What is exactly enthalpy of atomization? See, when you have an atom or when you have a molecule and you have to provide some energy and break them into smaller atoms, that is called as enthalpy of atomization. Okay, here you are giving some energy and you are breaking it, and now you are having two different atoms, right? That is called as your enthalpy of atomization. So now what I can say here is, see that the more the bond, the more stronger this bond is present between the two atoms, right? So it will become difficult to separate them, so we will require higher enthalpy of atomization. So the same thing here is, along the period the enthalpy of atomization will increase, right? Very basic. Along the period what happens? Along the period size decreases, the nuclear force increases, so definitely the enthalpy of atomization will increase, and down the group it also increases. So here it is very important, down the group what happens? As we move along down the group, the metals become more heavier, right? So suppose you have here, I'll say manganese, sorry, not the manganese. So for example, we have here chromium and tungsten, right? They are in the same group. So this is 2 atoms of chromium and this is 2 atoms of tungsten. So chromium mass is lesser, so here the force of attraction is less. Tungsten masses are heavier, so here the force of attraction is very high. So definitely here the enthalpy of atomization required will be more. Clear? So that is the thing, along the period and down the group, both side it increases. And here also we can find an exception. You can see that along the period we are moving, but here we can see that the enthalpy of atomization for manganese has decreased. Again, what is the reason here? Because of its stable electronic configuration, it does not participate in the intermetallic bonding, or the intermolecular forces between 2 manganese atoms is very weak, so easily we can separate them, right? So that is the reason here. Next, coming to atomic radius. So this is very important to understand. See, okay, for this first of all you should understand what is screening effect. So I will explain the screening effect with a very simple example. Suppose here some students are sitting and here a teacher is teaching the class, right? So all of you can see the board. So just imagine that this is your nucleus, okay, and these are the electrons. So the nucleus and electrons, there is a good force of attraction here. Now what happens? Suppose you put a screen in between them, okay, so what will happen? The visibility will decrease, right, or it will become blurry in here. So when it becomes blurry, you can see that the force of attraction will decrease. Now imagine the same thing in this case. You have nucleus and you have the last electron here. There was a force of attraction before. Now when between this nucleus and the last electron there are more electrons present, okay, what will these electrons do? They will definitely hinder the nuclear force. So this last electron will experience less nuclear force or less attraction force towards the nucleus. So what will happen? The effective nuclear charge will decrease. Okay, that is your screening effect. Now in the size, when we are talking about the atomic radius or the size, it is affected by 2 factors. One is the force of attraction between the nucleus and the last electron, and the second one is your screening effect. I hope the screening effect is clear. Now how it is affecting, I will make you understand. So see, yes, now along the period, when we are moving along the period, okay, so the nuclear force of attraction is increasing, so size decreases, okay, so effective nuclear charge is more, so size keeps on decreasing. So scandium is there, then titanium, then vanadium, then chromium, then manganese. This is the size. Now when you reach here iron, cobalt and nickel, so here what happens? Here the see, I'll have, this is 2 factors, right? We have just discussed that we have 2 factors, that is, one is your effective nuclear charge. So this tries to decrease the size, and the screening effect. So if you see the nuclear charge will decrease or the nuclear force of attraction will decrease, then what will happen? This one will, the nuclear force of attraction will decrease, then the size, it cannot attract this electron, right? The size will tend to increase. So this factor tries to increase the size, this factor tries to decrease the size. Now in case of this one, in the first few elements, the screening effect, the effective nuclear charge is a dominant factor. It is dominating, and that is why the size is decreasing. When you reach iron, cobalt and nickel, okay, the D elements are now filled, right? The D electrons are now filling, and they are putting a screening effect. So because of this screening effect and the effective nuclear charge, it is almost balanced. So that is why the size remains constant. And when you move towards copper and zinc, the D electrons are now D10 electrons, right? They will shield completely the nuclear charge from reaching the last electron. So if there's the shielding effect is more dominant, so size will increase here. Okay, fine. Next we have, you can see the trend here, that we have scandium, titanium, vanadium, chromium, up to chromium, Manganese, the size is decreasing. Then we have iron, cobalt and nickel, they have almost a similar size. Then from copper to zinc it increases. Okay, fine. Next, down the group, what happens? Down the group, generally, as you all know, in normal periodic properties also, new shells are added. So if new shells will be added, normally the size will increase. So that happens in the first group, that is your group 3, right? But towards this one, when you see that this is your 3D or 4th period, 5th period, 6th period, 3D, 4D and 5D, right? So if you see here that the 3D and the 4D, 3D will be lesser than 4D, 4D will be lesser than 5D. But as we move along this side, the 4D and 5D size almost become equal. Now this is something because of lanthanide contraction, right? This is because of lanthanide contraction. I think I would have given that, yes. Okay, so now you can see here, now you can see here the when you reach lanthanum to hafnium, the 4f electrons are involved, right? So when 4f electrons are involved, they have very poor shielding effect, means they cannot, their size is so diffuse that they cannot shield the nuclear power from reaching the last electron. So nuclear power can easily reach the last electron, so it will pull the last electron and the size will decrease here, right? Okay. Next property is your ionization enthalpy. Okay, so ionization enthalpy along the period it will increase. So you can write down first thing here, increase in the ionization enthalpy along each series of the transition elements from left to right due to the increase in the nuclear charge. This is very basic thing. Next, the trend of the steady increase in the second and the third ionization enthalpy breaks for the formation of Mn2 plus and Fe3 plus respectively. So now if you see that Mn is there, okay, that is configuration is 3D, 5 and 4s2, right? Now if I have Mn plus, I want to remove one electron, so I will get 3D, 5 and 4s1. Now if you give Mn2 plus, okay, now what happens if you see that when you are removing one more electron from already a positively charged species, you have to require more electron, right? So this is suppose IE1 and this is IE2. So you generally you have to require for IE2 you require more energy. But once you see that Mn2 plus configuration is 3D5, okay, which is a stable half filled configuration. So that is why immediately or the manganese plus can easily release one electron to give you Mn2 plus, and that is why the ionization enthalpy decreases here, okay, and the same thing applies for even Fe2 plus to Fe3 plus, okay. So you can see here ionization energy of Mn plus is less than the ionization energy of chromium. Why am I comparing this one? So if you see along the period we have first chromium and then manganese, right? So manganese ionization enthalpy should be greater than chromium because along the period the ionization energy increases, right? So if I now take Cr plus and Mn plus, this does not hold. The Cr plus ionization energy is more than the Mn plus because in Mn plus we are getting the stable configuration, okay. The same thing applies for Fe2 plus to Mn2 plus. So if you see Mn2 plus and then Fe2 plus, right, along the period this is the element, this is manganese, after next element is iron, so along the period it should increase. But Fe2 plus to Fe3 plus is a 3D5 configuration which is very stable, right? So that is why what happens, it does not, it can easily get converted to Fe2 plus to Fe3 plus, whereas in Mn2 plus this is already stable and it does not want to go to Mn3 plus state. So here you will require more energy, and that is why this is not the sign, rather this is the sign, okay. Clear? Next, coming to oxidation states. So all the transition elements shows variable oxidation state. What is the reason for that? The main reason for that is that both the Ns and N-1d electrons can participate. So you have general, what is the configuration? N-1d 1 to 10 and Ns 1 to 2. Sorry, Ns, yeah, 1 to 2. So this is the general configuration, right? And now here what happens, these two electrons or these two orbitals can easily participate. Their energy level gap is very less. They both of them can participate in the bond formation, and that is why the oxidation state is so wide. Variety of oxidation states are available. Now if you see, you can see the manganese is the element with highest number of oxidation states, that is from +2 to +7. Okay, and one more important thing here, the higher oxidation states are more stable down the group. So if you see chromium 6, molybdenum 6 and tungsten 6, tungsten 6 and molybdenum 6 are more stable than chromium 6. Okay, then one more important thing, you have to see the exception here, scandium and zinc, they do not have variable oxidation state. Scandium has only one state and zinc also has only one oxidation state. All other elements have more than one oxidation state. Okay. Next, moving to, yes, this is very important and my favorite part, that is your reduction potential. So along the reduction potential means what? Reduction potential means tendency to gain electrons, right? If you can gain electrons easily, you can get reduced easily, your E0 value will be higher. Along the period, what we have seen, the electronegativity, the size generally decreases, so the reduction potential along the period will increase, right? So becomes less negative along the period. Less negative means, suppose it is starting from -4, then -3, -2, -1, 0, like that it will become less negative along the period. Okay, now if M to M, so this is what I have written in my own words, if M to M2 plus is easy, okay, then E0 value will be more negative. See, this is what? Oxidation. Okay, so if oxidation is easy, then E0 value will be negative. If reduction is easy, then E0 value will be positive. Okay, so you can see here that as we see from titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, along the period it will become less negative. So first we have -1.63, -1.18, -0.9, but here you can see again it is increasing. So which element is that? Manganese. So there is a special treatment or special reason for that. Then again it started decreasing, again decreased here, again decreased here. Again here we have increased near copper. Okay, here also something special is there. Then if you, and here you can see it is a completely positive value, right? And then again it decreased. Okay, so what are the reasons here? Yes, you can see the exceptions here. So nickel, what is the exception is, you can see how much it was decreasing from -0.44 to -2.8 we got, but after that it became -0.25. So there is very less decrease. How much decrease was expected, that much was not there. So these are the three exceptions present in this table. One is your manganese value, then you have Ni value, and then you have copper value. Okay, so okay, so now what can be the reasons for this? Let's discuss. Okay, now see, reduction potential, right? Reduction potential M +2 to M. So very simple, if the reduction is easy, if the reduction is easy, then E0 value will be high. Okay, reduction is difficult, then E0 value will be less. So you can see that here from -0.9 to -1.18 means what happened here? Here the value has become more negative, means here the reduction is difficult, right? You can see the value has become more negative, reduction value has decreased here, right? -0.9 and -1.18, reduction value has decreased, that means reduction is difficult. Why is it difficult? Very simple. So what you are actually reducing? Mn2 plus to Mn, right? So here I have already told you this is a stable D5 configuration. It is very happy in its D5 configuration. If you forcefully take it to Mn condition, it is not happy with that, right? So that is why it is showing resistance to reduction and the reduction value decreases here. Clear? That's the first thing. Next, for nickel here we have a different reason, that is your hydration enthalpy. Okay, for nickel you have to remember the hydration enthalpy. Next, if I talk for copper 2 plus, okay, now copper to copper 2 plus if I talk, okay, copper to copper 2 plus, when you are removing the electron for this one, right? So for copper, first you will get copper plus, and then you will get copper 2 plus. And when you're doing this one, this is your 3D10 configuration. We are making it D9. So you have to provide a lot of energy here. Okay, so that is why the reduction potential becomes positive. So basically, if you remember, E naught value is affected by 3 factors. One is your enthalpy of atomization, then you have reduction enthalpy or reduction value, and next one is your next one is your hydration enthalpy, right? So in this case, this E naught value of copper is very, very high. Okay, especially, sorry, not E naught value, I'm right, ionization enthalpy, yes, atomization, ionization and hydration. So the ionization value is very high for copper plus to copper 2 plus, and that is why you get a positive E naught value. For nickel, we are getting here because of the hydration enthalpy. Clear? Okay, next, M plus 3 to M plus 2, this is also very important topic and my favorite. So again here, if M plus 3 to plus 2 is easy, okay, if you can easily convert it, or if it is a happy conversion, then E naught value will be higher. If it's a difficult conversion, then E naught value will be less, right? So if you see here, Sc plus 3 to Sc plus 2, scandium 3 plus is your exactly configuration of argon, noble gas configuration. It's already in a happy state. You are converting it into a less stable state for low value, so that is why the E naught value will be very less. So why? Because stability of Sc plus 3 is more. Then if you see next one, that is Zn plus 3 to Zn plus 2. Zn plus 2 is more stable, right? Because plus 3 is Zn plus 2 is D10 configuration, very stable configuration. So what will happen? If it is getting easy, you are getting from a less stable to more stable, right? So it is a easy conversion, so that is why high value because of the stability of Zn2 plus. Next, Mn plus 3 to Mn plus 2, again Mn plus 2 is more stable, right? So easy conversion here, that means stability of Mn2 plus is more, easy conversion, so high value. Fe plus 3 to Fe plus 2, Fe plus 3 is more stable, so more stable to unstable you are going, so that means you are converting from stable to unstable, right? So that is a difficult process, not an easy conversion. E naught value will be low here. Okay. Next, if I see stability of higher oxidation state, so here you should be knowing certain things. Okay, so generally the higher oxidation states are stabilized by fluorine and oxygen. So why do fluorine do that? Fluorine do because of its high lattice energy and high bond enthalpy. High lattice energy example is COF3, means cobalt in plus 3 oxidation state is stable because of the high lattice energy of fluorine. And here you can see VF5 and CrF6, and here the VF5 and CrF6 are more stable due to its higher bond enthalpy. Clear? Next, we have fluorides are unstable in the lower oxidation state. You can see the example here. So you can find out like VCl2Br2I2, but VF2 is not available. Similarly, CuClBrI is available, F is not available. Next, CuX2 are known except your copper iodide. Okay, so CuI2 means CuCl2F2Br2 you can find, but CuI2 is not available, and there's a reason for that. The Cu2 plus can easily oxidize the I minus to I2. So you do not get this I minus get oxidized to I2, so you don't get CuI2, you get Cu2I2. Yeah, this is something you should be knowing. Next, we have copper compounds are unstable in the aqueous medium, so it gets disproportionation reaction. So actually Cu plus, if you see, it is a D10 configuration and this is D9 configuration, but in reality this one is more stable. Why? Because of high negative hydration enthalpy. Okay. So the stability of Cu2 plus rather than Cu plus is due to the more negative hydration enthalpy of Cu2 plus than Cu plus. Clear? Next property is, okay, here we have some more. So if I compare oxygen and fluorine, okay, the oxygen is the element which can stabilize the higher oxidation states better than fluorine. What is the reason for that? That is because of, you can see the example, manganese can with fluorine can form MnF4, where its oxidation state is +2. With oxygen it can form Mn2O7, where its oxidation state is +7, right? So the ability of the oxygen to form multiple bonds with the metal explains its superiority. So it can form multiple bonds, double bond can be formed by oxygen, and that is why the elements are more stable with oxygen. Okay. Next we have magnetic properties. So magnetic properties, you know, should be of three types: paramagnetism, diamagnetism and ferromagnetism. So if you have any unpaired electron, so what is paramagnetism? They are attracted in the presence of magnetic field. Diamagnetism, they are strongly attracted in the presence of magnetic field, strongly repelled, and ferromagnetism, they are, okay, here is a mistake, this is this one and this one, okay. So repelled by the magnetic field is your diamagnetism. Ferromagnetism is strongly attracted in the presence of the magnetic field, okay. So please exchange this one. And paramagnetism, when can you find? When you have unpaired electron, okay. And diamagnetism, when you have no unpaired electron. Okay. Next, the formula to calculate the magnetic moment is mu is equal to root over of n into n plus 2, okay. And n here is what? N is here is number of unpaired electrons. You can get numericals from here, so definitely you should be knowing this one. And here also I want to tell you a trick. Okay, I haven't mentioned that. Okay, so if n is equal to 1, magnetic moment will be 1.7. For 2 it is 2.7. For 3 it is 2.8. This is 3.9. For 4 it is 4.9, and for 5 3.8, and this is 5.9. Okay, so you have to remember this one. More than 5 unpaired electrons you cannot get, because after that again pairing will start. Okay. Next we have color compounds. So generally what happens, the D block elements are colored compounds, and that is because of your DD transition. So we have already studied in coordination compounds what happens when a transition metal is there and ligands are approaching to this one. The D orbitals of this transition metal splits into two parts, T2G and EG. Right now what happens, because of this splitting of the d orbitals, the electrons are present, and these electrons can undergo transition, and this transition takes place in visible region. So that is why these are your colored compounds. Okay, what is the reason? Because of DD transition. Next we have complex compounds. So transition metals can form a lot of complex compounds. You have seen all these examples are there. Okay, then what is the reason for that? So you should be knowing this in points. This is very important. It can be given in terms of MCQ. So first is small size, high ionic charges and availability of d orbitals. Next we have the catalytic property. This is again very important. So what is the reason for catalytic property? You can see they can have multiple oxidation states, ability to form complexes, and we also have their availability of d orbitals. Okay, and example you can see vanadium V2O5 is used in contact process. Contact process is a process by which we can manufacture sulfuric acid, H2SO4. Okay. Next, here we have the interstitial compounds. So interstitial compounds, you can see that when the elements are present, there are some gaps in between, right? So when these gaps are filled by other small atoms, then we call it as an interstitial compounds. Now in interstitial compounds you can see the examples, and transition elements are generally can form interstitial compounds because of the gap present between different atoms, and this helps to improve their properties. Like what can we see, their metals become very hard, they retain their metallic conductivity, they are chemically inert, and they have high melting points. Okay. Next we have alloy formation. So alloy formation, because I told you that their size is not very much different, the sizes are similar, so the atoms can be easily mixed and we can have a lot of alloys from this one. The two very important examples are your brass and bronze, right? You can see the examples here. Next, coming to oxides and oxoanions. Okay, So first of all, the transition metals form oxides at higher temperature, and all the metals except scandium form MO oxides, which are ionic. Okay, so very important, scandium does not form oxides, all other elements form ionic oxides generally. Now as the oxidation number of a metal increases, the ionic character decreases and hence the melting point decreases. Okay, this is again very important point. So as the oxidation number of the metal is increasing, okay, the bond is becoming more and more covalent now, so the melting point will decrease. Okay, so you can see here that CrO3 and B2O5 have low melting point because their oxidation states are very high. Next, here we have something that is these are the oxides of manganese, MnO, Mn2O3, MnO2 and Mn2O7. So if you see that here the oxidation state is +2, here it is +3, here it is +4 and here it is +7, right? So now as you see this bond or this one here, the compound is more covalent, right, and here it is ionic, right? So if it is here ionic, along the period what happens, the ionic character will decrease and the covalent character will increase. Okay, and you can also see that liquid at room temperature. So generally here it will be in the form of solid, and as we move the compounds will become covalent and they will become liquid. Okay. Next we have about the acidic nature. So when the oxidation number of the metal will increase, the acidic character will also increase. Okay. Okay, so here we have the examples. You should remember these examples. Okay, so these are your acidic oxides. Okay, this is your amphoteric and this is basic. Okay, similarly here also acidic, amphoteric and basic oxides examples you should be knowing. Okay. Next property here is, we'll go to the next topic, that is important compounds. Here you have to remember two important compounds, K2Cr2O7 and KMnO4. About that, what all things we'll be studying? Their preparation, their structure and their chemical reactions. So preparation, I think all of you would have already studied. I'm not going to explain this one. So methods of preparation of your potassium dichromate. So you have to take iron chromate, right? This iron chromate is converted to sodium chromate. Sodium chromate is converted to sodium dichromate. Sodium dichromate is converted to potassium dichromate. Okay, so that is the method of preparation. Structure, talking about the structure, they both have your tetrahedral structure. So this is CrO4 2- and this is Cr2O7 2-. Next we have the chemical properties. So generally CrO4 2- can be converted to Cr2O7 2- by adding H+, and similarly Cr2O7 2- can be converted to CrO4 2- by adding OH-. Okay. Next we have here, you can see the same thing, we have represented this one. So these are interconvertible. Okay. Now KMnO4, okay, just a minute. Yeah, sorry, this is a small mistake. This is K2Cr2O7. It is a very good oxidizing agent. Okay, it can oxidize any species. So you can see here we have so many reactions. You just have to remember what is getting oxidized to what. So I- gets oxidized to I2, H2S gets oxidized to S, Sn2 plus to Sn4 plus, Fe2 plus to Fe3 plus. So these are the conversions that you should be remembering. Next, potassium permanganate. If you see, we have two methods of preparation. So first one is using MnO2, you convert it into K2MnO4 permanganate, manganate, then manganate is converted to permanganate. Okay, MnO4-. So another commercial method is also there, where you take MnO2, you fuse with your KOH, oxidize with air, or KNO3, you get manganate ion, then with electrolytic oxidation you convert it into permanganate ion. Okay. Next we have, okay, so we have two commercial methods here. So one is from Mn2 plus also we can get, and another one is your MnO2. So these reactions you should be remembering, not exactly, but the products and the main products you should be knowing. Okay. After that, structure, these all have tetrahedral structure. This is MnO4 2-, this is MnO4-. Here a question is asked, that is, this is your manganate, MnO4 2 minus, right? This is manganate and this is permanganate, which is MnO4 minus. Okay, the symbol is there. Color also you should remember, this is green color and that is purple color. You might have seen this in your labs very often, right? Permanganate ion. Next, chemical properties. This is also a very good oxidizing agent, okay? But potassium permanganate forms dark color crystals which are isostructural with KClO4. This is also a very prominent question where it is asked which of the following is isostructural with MnO4. So please remember it is KClO4. After that, its intense color is due to the charge transfer. Now here a very important question arises. If you see manganese, permanganate ion in MnO4 minus, the manganese oxidation state is +7. What is the electronic configuration of manganese? Argon 3d5-4s2. If I have manganese in +7 state, then it is only argon, right? So there is no d electrons. If there is no d electrons, there won't be any dd transition, there won't be any color, but still it is so bright in color, and that is only because of charge transfer and not because of dd transition. What is charge transfer and all is a higher level thing which you need not know. You have to just understand that there is something called as charge transfer, ligand to metal charge transfer, because of which this is a colored compound. Next, it shows weak temperature dependent magnetism. So generally if you see there is no unpaired electron, so it has to be diamagnetic, right? But sometimes it even shows some magnetism effect due to some temperature effect. And after that, it also undergoes thermal decomposition. So you can see here KMnO4 decomposes to give you K2MnO4, MnO2 plus O2. Okay, fine. Next, if we move towards the chemical properties, so this is very important. Here manganese or manganate ions, permanganate ions can behave differently in different medium. So first of all, in your acidic medium, okay, permanganate ion gets converted from +7 to +2. In neutral medium, the +7 goes to +4, neutral medium, and here from +7 it goes to +6. Okay, so you can see +7 to +2, +7 to +4 and +7 to +6. That is a basic medium, neutral medium and acidic medium. So it behaves differently in different medium. That is what you have to remember. The same thing is also applicable when it is oxidizing other species, right? So basically if you are taking an acidic medium, so you will find the reactions like this, yes, where I minus is getting converted to I2. So this is important reaction from where questions have been asked repeatedly. I minus gets converted to I2, NO2 gets converted to NO3, SO3 gets converted to SO4. Apart from this, we have these example as well. S2 minus gets converted to S, Fe2 plus to Fe3 plus, C2O4 2 minus to CO2. But when it is a neutral medium, you can see the difference. Okay, you can see the difference in this one. Iodine, I minus gets converted to IO3 minus. Okay, S2O3, there also it was SO4, here also it is SO4, and Mn2 plus gets converted to MnO2. Clear? Okay, now talking about lanthanoids. So what are lanthanoids? So as we have seen in the starting of the video also, there are some elements which are placed below the periodic table. Okay, and these two series which are placed below the periodic table are your lanthanoids and actinoids. So lanthanoids form the first one. These are also called as your 4f series because the last electron enters to the 4f orbital, and this is your 5f series, that is your actinoids. Okay, so lanthanoids, what are the things that we have to study? The last electron enters the 4f shell. They are also called as rare earth metal, and the general electronic configuration is Xe4f1 to 14. So let me write down it properly here. Xe4f1 to 14, 5d0 to 1, 6s2. Okay, next here you can see the configuration of lanthanum. Okay, so you don't have to remember all the configurations, but I am highlighting certain elements whose configuration you should be knowing. First one is your cerium, then you should be knowing for europium, gadolinium. Okay, then you have for terbium and lutetium. So these 1 to 5 elements electronic configuration. Please remember these are important. Okay. Next, moving to your atomic sizes. So here what happens, along the period it decreases. So generally it decreases along the period, but the decrease become more prominent here because of your lanthanide contraction. Okay, and what is the reason of lanthanide contraction? The poor shielding effect of 4f orbitals. Next, what happens, the consequences due to this, these element size becomes almost same to each other. Okay, similar size, difficult to separate, right? Then we have the basic character along the period decreases, okay, because the bond becomes very strong and the OH minus ions cannot be released easily in case of lutetium. Next, 4D and 5D radii are similar. You can see the example, zirconium and hafnium, Nb and Ta, molybdenum and tungsten. These sizes are very much similar because of your lanthanide contraction. Okay. Next, here we have oxidation states. The common oxidation state is generally +3, but it also shows +4 and +2. Which element shows +4? So you have Pr, you have to remember this one, Ce +4, this you should be remembering. And which one shows +2? Sm, Eu, Tm and Yb. Okay, so there are 4 elements which can shows +4. Out of that, this Ce +4 is very easy and important, because Ce in +4 oxidation state gains a stable oxidation stable configuration of noble gas configuration. And here you have Eu2+, that is also important. Next, we have color compounds. Here instead of DD transition we have FF transition, so color depends on number of unpaired electrons. Here we have a very special feature, 4Fn and 4F14-N have the same color. Okay, that means suppose if I take 4F, I'll take for example 4F6, okay, and 4F8. Okay, they both will have same color, and 4F0 and 4F14 are colorless. That is very obvious because of absence of unpaired electrons. Okay. Next, coming to magnetic properties. So you don't have to remember anything here. The most paramagnetic material is your Nd, and here you have lanthanum and lutetium. These are diamagnetic. Ce +4 and Yb2+ are diamagnetic because they don't have any unpaired electron, and all other lanthanum 3+ elements are paramagnetic. Okay. Next, chemical reactions of lanthanides, not have to go much in detail, very simple you have to remember. Lanthanide has +3 oxidation state, right? So how can I just write down? If it is burning with oxygen, so lanthanide is +2, oxygen is -2, let me do crisscross, I will get Ln2O3, right? Next, coming to sulfur, sulfur also 2-, so you will get Ln2S3. Nitrogen is 3-, so +3 -3 will get cancelled, you will get Ln. And with carbon, so lanthanum with carbon you should remember, okay, so you will get LnC2. Okay. Next, with water you will get lanthanum hydroxide. With halogen, so lanthanum is +3, halogen is -1, then do again crisscross, you will get Lnx3, and with acids it will give you hydrogen gas. Uses, the most important uses of lanthanide is to prepare an alloy, that is your mic metal, where you have 95% of lanthanide, Fe 5% and traces of sulfur, carbon, calcium and aluminium. Okay, fine. Next, actinoids, already I have shown you where is lanthanide. The next series below that is your actinoids, and they have a general electronic configuration. So in actinoids, almost all the elements are radioactive. The last electron enters the 5f shell. So what is the electronic configuration here? You have 5f 1 to 14, 6d 0 to 1 and 7s2. Okay. Next, we have the electronic configuration here. You can see here also I will say which all elements you should be remembering. The first 2 definitely. Okay. Next, you have here this one. Okay, americium and curium, and then you should be remembering for nobelium and lawrencium. Okay, so these 5-6 elements electronic configuration you should be remembering. Again, the trend here, atomic size will decrease along the period. That is due to your actinoid contraction, and actinoid contraction is due to the poor shielding effect of 5f orbitals and not 4f orbitals. And what are the common oxidation state? The common oxidation state is +3. Highest oxidation state is shown by +7, that is MP and PA. And the stable but these are unstable. Okay, stable higher oxidation state or stable highest oxidation state is shown by your uranium. Okay, yes. So students, this was the most important things, the most important concepts from this particular chapter that you should be knowing. So please revise this. Then in the next video we'll be doing the coordination chapter, and I'll be releasing a top 30 MCQs video on D and F block. So please prepare this and go and solve those 30 questions. Then this chapter is done for you. Okay, so that's all students, and see you soon in the next class. And I hope you have made all the notes. So please prepare hard. We are just left with 25 days. Do not waste even a single day at this point of time. So thank you for watching, and do not forget to subscribe the channel.